And I had to do this when I worked at Raytheon Company, because I was working on some products that had to be safety critical. And so I had to figure all this out, and that's the reason I'm able to give this lecture. Okay. The intent of this first part is to explain what we mean by software safety and how software can contribute to safety problems and what techniques are used to deal with that and to write safety critical software. So the way it's going to work is this is an outline of the 2 days. Part one, we're going to talk about some background information and then discuss how software can contribute to safety. And then we're going to have exercise one. That'll be about 10:30 today. And exercise one is something you will do during the break. We will have a break for about half an hour. And during that break, you will have a break, and then you will have time to work on exercise one. And then after we return from exercise one, each student will give a very brief presentation on their solution to exercise one. There is a handout called exercise one available to you, and it explains what you're supposed to do. And there's another handout out there that explains which student does which topic on exercise one. So at your convenience, you should obtain those two things. Then after the break today, we will have a discussion of the safety process, the overall process for how organizations deal with safety. And then we will have the introduction to exercise two, which you will do as homework. And then on Thursday, you will present your solution to exercise two. And I'll say more about that when we get there. Then on Thursday, we'll do part two, which is all about the things we can do when we are writing and designing software to properly deal with software safety. So let's begin with the background. One of the first questions that often comes up is, why should we even worry about software safety? How can software hurt anybody? I suppose there are some people who will jump on a chair and scream if you say the word software, but not too many of us. And the issue with software is a little more complicated. It turns out that software by itself is pretty harmless. It's just like there's an old joke that the reason there's so much software on airplanes is that you can write billions of lines of code and it doesn't weigh anything. But anyway, let's talk about the organizations that are concerned about software safety and then get some insight as to why they are concerned. Air travel. Basic idea with air travel is if software is controlling a lot of the airplane, then if the software has a mistake, the airplane may not fly. Military applications where you're using very dangerous equipment, you have to be very concerned about safety issues or somebody might get hurt. Power generation, especially nuclear power, where you have a very high level of energy being controlled by machines and computers. The software is doing a lot of that control. And there are some very interesting examples out there of software, for example, trying to run a nuclear power plant and they didn't do it right and it caused considerable danger. Transportation, including modern automobiles. When you have something in a car that's supposed to do something, think about the Tesla, all the software in a Tesla. And if it goes wrong, you end up with a crash. And dam construction, you may not think about this, but it turns out that there's very interesting problems with software related to the way dams function and the way they are built. Medical devices, you can certainly imagine that. I will be giving an example a little bit later of a situation where I was under surgery, and the surgery was being performed by a robot controlled by software. Made me very aware of this problem. These and more things deal with what are called potentially dangerous equipment. And the word potential is really an important word there, because it tells us that whether or not it turns out to be a problem, whether or not it turns out to be dangerous, may have a lot to do with the software. And more these days, we control this kind of equipment with software. Let's look at an airplane. About a third of the development cost of a modern aircraft is for software. Now, I've already given you the joke about that's because it doesn't weigh anything. But the point is that that's an awful lot. I mean, you think about all that goes into an airplane, and 1/3 of the cost is software. That's an awful lot of people writing an awful lot of software. Over 80% of the functions in an airplane are performed by software. Now, this is not necessarily measuring them by complexity or whatever, it's just by number. And in many cases where they claim it was pilot error, it involves software. For example, the pilot didn't understand what the software was trying to get it to do. We've all run into that problem. I just had it a few minutes ago trying to figure out how to share my screen properly. Imagine you're flying an airplane in a dangerous situation and you're not quite sure how to make the software function. So that's a situation where the software problem was not that the software was incorrect. It was that they didn't have good human factors engineering when they designed the software, and so didn't understand the proper way to interface with the pilot. The Boeing 737 MAX problem of a couple of years ago, a lot of the news articles claimed that it was software that was causing the problem. It was actually a little more complicated than that, but software was certainly involved. Here are some key findings from the Boeing 737 MAX situation. One of the first findings, and this is often a problem with safety-related software, Boeing rushed the product to market and therefore cut corners in order to meet deadlines. That is a fatal mistake when you're dealing with safety critical software. And if you've ever worked for a real company writing software, or even as a student writing a program that's due tomorrow or something, you need to allow yourself with enough time to not have this problem. Boeing cut a lot of corners. For example, the training, that's an area where they cut back, and turns out that it was a really big mistake. They didn't spend the time to develop a good enough training system. Normally, pilots are trained in simulators, and they get hours and hours of training. Somebody decided that they could train for certain features they were adding to this airplane with a 2.5-hour iPad course. It turns out it didn't work very well. The system that was having problems was called MCAS. It was all implemented in software, and it was blamed for the failings. But the reason it failed was that both Boeing and the FAA, which is supposed to regulate these things, were reluctant to properly inform pilots about how to deal with it, or to properly apply the safety critical type regulations. So in other words, the fact that it was implemented in software was part of the problem, because there was some software problems. But the other problem was that people didn't implement the safety regulations that they should have. The FAA has admitted to being incompetent when regulating software. Now, this is a really important point. I discovered this 20 years ago when I was working on a safety critical application for Raytheon Company. In effect, the FAA has not been funded enough by Congress. Congress is always very good at funding things that they think will get them votes, and not very good at funding things that really are important but are in the background, such as giving the FAA more money so they can improve their competence with regard to regulating software. And so one of the problems was that they didn't even mention this new feature in the paperwork that they use to get the thing certified, which they certainly should have. This is a graph I pulled out a number of years ago, but it's very interesting. It talks about the percentage of the functions performed by software in United States Air Force airplanes. And you'll notice that by the year 2000, it was 80%. And it's probably more today. I don't have a more recent graph, but you can see how much has changed since the 1960s, when there was almost no software. In fact, I remember those days because that's when I got involved with software, and the computers they had on airplanes were so heavy they could do so little. I mean, they had a computer about the size of a refrigerator that could do less than your smartphone. Anyway, sometimes what the software does is quite sophisticated. For example, center of gravity control. They have to control where the fuel is, because the fuel is carried in the wings, and they have to keep it balanced so that they don't put too much stress on one wing while the other wing isn't getting as much stress. It's actually a non-trivial issue there. Okay, now modern automobiles. It's interesting how you might really be surprised, although I've seen some advertising on TV where the guy says you need to have a PhD in order to do maintenance on a modern car. Well, that's an exaggeration, but the point is that there's an awful lot of software in a modern car. 25% of the capital cost is for computers and software. And most of that is for the software. All kinds of different parts of a car have to have software in modern cars. Here's an ad from IBM that I tore out of a magazine. You can't read it very well, but the whole point of the ad is how much computer stuff is going on inside of a car. And of course, IBM is advertising about their software capabilities. Okay, now let's turn to medical equipment, one that I'm more familiar with than I wish I were. Many modern medical devices are controlled by software. It's highly computerized and highly dependent on that software. This is an MRI machine. I've been through that a few times, and it basically rotates magnets around that big circle there, and then they somehow or other figure out what's going on inside of your body. And it's a kind of an intimidating experience, because you go inside this big circle and then you just sit there for a while this noisy thing keeps rotating around. But the point is that it wouldn't work without software. Now, this particular device can't do any harm, but that's not true for all medical devices. Computer-aided surgery is becoming quite common. Why? It's less invasive than a human, because the computer can be more precise than even the finest surgeon in terms of exactly what to do when and where. It has lower hand vibration, highly accurate positioning, and it reduces the physical burden on the patient. I have had this type of surgery twice now, and in both cases, the doctors have told me your recovery would have been a lot more uncomfortable if we hadn't used the computerized robot. That's what the computerized robot looks like. They don't wheel it into the room until you're unconscious. Why? Because most people will look at that and start getting anxious. But in fact, that's what does the job. And it is used in all kinds of applications. There are more than 2,700 installations, and actually I haven't updated that number. It's probably a lot larger than that now. It's called the Da Vinci Surgery System. And look at all the things it's used for. I used it for 2 different kinds of surgery in my own situation. And it really improved surgery quite substantially. But of course, you have software controlling every little thing that it does. Now, let's look at the future of computers and software in medicine. It's often presented as a robotics thing. Robots will do all these things. But in fact, it's software inside those robots that's really what matters. For example, doing checkups, diagnosis, and even therapy remotely, like by Zoom, like we're doing this course today. Imagine an elderly patient or a pregnant person trying to not have to physically go to see the doctor because it's too much of an effort. Maybe they can do it all online. What about situations where you are not conveniently available to a hospital? You're way out in the desert, or you have an accident in Africa, out in the jungle somewhere or whatever, or you're on a cruise ship and you suddenly have some kind of a medical emergency that the cruise ship isn't equipped to handle. Well, they're already implementing telemedicine, where a surgeon or other medical expert can be in a hospital somewhere, and you can be anywhere as long as you have the internet and perhaps some more simplistic devices available. And they can take care of you, at least to some extent, remotely. There's even talk about doing surgery remotely, putting a Da Vinci machine in your cruise ship and then have the surgeon be back home in Dallas or something. All right. Now, all this software is developed by people like yourselves, software engineers. And this is why so many software engineers are needed today, because there's software in all these different kinds of products. But normal software development is often kind of like Wile E. Coyote, and if you've ever seen those Roadrunner cartoons, with some way to make it work, sort of, or hope that it'll work. You can't do that sort of thing with safety critical software. It's really vital for the software to operate correctly, or at the very least, in a manner that won't do any harm if something goes wrong. It has to do this all the time under unexpected circumstances, under conditions of operator error, and under conditions of hardware error. So you can get pretty complicated there. You can't do it in the simplistic way that you may be able to get away with if you're just putting a video game on a smartphone. Okay, so what's different about software development with our safety critical software? The gist of it is that it's more rigorous development practices. It involves all kinds of things, like the words at the very bottom there, to make it much less likely that you're going to have a safety problem. Now, what are some characteristics of safety critical products? There's intense focus on identifying ways the system can fail. So the very first thing you do is say, how could this thing go wrong? And then what could we do to keep that from happening? There's rigorous processes for developing the software. Every step of the way, from understanding the requirements to implementing and developing it and delivering it and installing it, making sure that you cannot make a mistake, or at least reduce the likelihood. Another element is what they call independent audits. That means somebody other than the people who developed the software reviews and audits what they did to make sure they didn't miss anything. Sometimes they mistakenly overlook a step or something like that. Rigorous safety standards have to be established. And this is an area where different kinds of products have different standards. I'll say more about that in a moment. But all of that is not enough. You also need to think differently about what you are doing. It requires a kind of a mind shift in terms of the software developer. You have to think at the system level instead of the component or module level. That is a picture of a power grid and all the different parts that have to be interconnected in order for it to work properly. Think about all the ways something could go wrong on something that complicated. And you have to imagine and think through, well, what if this thing over here makes this mistake and sends that message to that thing over there? What could happen? And as we build more and more complicated systems, we find more and more risk associated with just the sheer complexity of the system. Now, software often replaces hardware and sometimes replaces people, especially with all the AI that they're talking about these days. Many software tasks were once done in hardware or by people, and in many cases, the software does this, but the functions are often very dangerous. Sometimes they are too quick for people to be able to do them. For example, anti-lock brakes function because software is faster than people could possibly be in terms of knowing what to do with the brakes under certain situations. And I remember seeing a little thing on the TV where a really experienced race car driver who thought he knew how to do all these things was being compared with a computerized vehicle doing some of the same maneuvers. And the race car driver realized that he couldn't keep up with the computer in terms of quickness and of response and things like that. Here is an interesting example of what can go wrong. It's the Therac 25, a radiation machine that was developed in the 1980s in Canada. And it was computerized, it had software in it and so forth and so on. Now, this machine was designed to do two things: to do analysis of situations by sending very low doses of radiation, and to do curing of certain cancers by sending in high doses of radiation. One of the mistakes was having a machine that could do both of those at the same time. It seemed like a good idea since most of the equipment needed to be the same, but it turns out there was a safety issue we're going to talk about. It was involved in at least 6 accidents in the late 1980s in which patients were giving much too much radiation. Either they were supposed to get a certain amount and they received more, or they were supposed to have a small diagnostic amount and instead they received a large therapeutic amount. And it turns out it was due to concurrent programming errors. Now, I'm very familiar with some of them because I've spoken with some of the people who did some of this and did the analysis of the problem. It sometimes gave its patients radiation doses that were hundreds of times greater than what they should have received. Sometimes it resulted in death or serious injury. So it was a big deal. Now, a commission was established to conduct a study. The commission was headed by a lady named Nancy Levison, whose name is at the bottom. At the time, she was at the University of Washington, but she has since moved to MIT. And in fact, I've gone to one of her seminars. She has an annual software safety sort of a conference, almost a 2 or 3 day thing. And I went to it one time, and it's quite interesting. Anyway, they concluded that there were software design and development problems. Notice that it was not just the design, it was also the development practices. It was not due to coding errors. It was designing the software so that it was impossible to test it in a clean and automated way. So it wasn't that they made a mistake in their programming, it was a mistake in the design that made it impossible to test it properly. Now, you don't necessarily think about that when you're writing your software, but that was what they found. My experience with the people who worked on this is that one of the problems was that there was a situation that the operator got into that the software designers had never anticipated, and therefore they didn't have it function properly under those conditions. All right, now let's talk about how software contributes to safety. Software can control the behavior of dangerous devices, and there's some listed on the left. There's lots of things going on in the world that are very potentially dangerous. Imagine a chemical, manufacturing plant. Remember Bhopal, India? Some of you are too young to remember that, but it was a huge chemical manufacturing plant in India that blew up and killed hundreds of people. Medical devices we've already talked about. Security doors in buildings, something as simple as that. There's all sorts of products that are potentially dangerous, and software often controls some or all of that behavior. But it can also send information that is wrong or dangerous. And it can send information to people or machines that do dangerous things. And if they get the wrong information, they may do the wrong thing. For example, sending data to an air traffic control system about where the airplane is. If you don't send the right information, you can issue the wrong commands to the pilot. There's all sorts of examples like that. It can also deceive. We're all familiar with internet scams. And there are many, many more things. The people who are intent on criminal behavior are always one step ahead of us in terms of thinking of ways that they can get around a system. And we software people have to be clever enough to anticipate what they're doing and prevent it. Now, what do we mean by safe software? Well, probably the normal person probably thinks, well, if it's safe, it can't possibly do any harm. Well, it turns out you can't design systems like that. So the people in the safety industry have defined safety in a slightly different way. First of all, the software has to have features and procedures that ensure that it performs in a predictable way under normal and abnormal conditions. In other words, it doesn't behave in a way that you cannot expect it to behave. Then the likelihood of an undesirable event is minimized. In other words, we don't say it can never happen. We say it's extremely unlikely to happen. And if an undesirable event does occur, the consequences are controlled and contained. In other words, you try to make things as unharmful as possible if things go wrong. Now, those are safety standards that were developed for hardware devices long time ago, and are basically considered the basis for the definition of what safe software is. Okay, now here are some key concepts. No software-based safety critical system is 100% safe. In other words, we minimize the likelihood of a problem and we minimize the consequences of a problem, but we can't guarantee that it will never, ever, under any circumstance, go wrong. And there are all sorts of reasons for this. For example, you can't possibly test all possible conditions or prove that all circumstances are covered if you're building a truly complex product. You can try to prove a program is correct, and that's actually used by some people for software safety type purposes. But even there, you have, anytime you have a proof of correctness, you have certain assumptions in your proof, and if your assumptions turn out to be wrong, then you're going to be wrong. Safety experts, instead of trying to guarantee 100% safe, they focus on two questions. First of all, how likely is it to fail? And secondly, if it fails, how severe will the consequences be? Those are the two things that you really focus on. That's the goal, is to have both of those be very low. Software safety can only be evaluated within the context of the system that the software is part of. One of the most important things I learned working in industry is that software is always part of some bigger system, and you have to understand the bigger system in order to do the software right. And the consequences, pardon me, I've got something in my throat today. The consequences of your software may be influenced and affected by the nature of the system you are part of. Sometimes it's very simple. For example, one of my pet peeves is somebody will take an application from a computer and try to put it on a smartphone and not even bother to change things like the sizes of the letters in the words. And so you get something that you can read on the screen of your computer, but when it's on your smartphone, it's so tiny you can barely read it. That's an example of paying attention to the system you are part of. This includes the people you are going to interact with. And of course, people are very difficult to understand the behavior of. I once worked on a application called Pilot's Associate. It was supposed to take over control of an airplane if the pilot fainted or was made unavailable to fly the plane. That sometimes happens in jet aircraft and fighter aircraft, where the pilot does some tricky maneuver and it makes them unconscious for a while. And it turns out it was really easy to fly the plane. The hard part was deciding whether and when to let the pilot take over when the pilot recovered, because the pilot thinks he or she is able to fly the plane when in fact they're not. That turns out to be a really difficult situation to deal with. But anyway, I mentioned at the beginning that there are a lot of different standards. This is some of the existing standards in more major products, the more widely used standards. And the point here is there's over a dozen standards listed there, including a whole bunch of them in the medical world. And the problem is that each of the standards bodies does things differently. So if you're working on an aircraft, you do things a little differently than what happens if you're NASA. And if they're there, it's a little different from what happens with medical devices. This lecture today and Thursday is focused on the commonalities from all of these. But I emphasize that there are differences and you have to focus on the specific standard. For example, some of the things that matter a whole lot in aircraft may not matter as much in a nuclear power plant, and vice versa. Okay, what do these standards specify? First of all, they typically specify processes and procedures that you should follow when developing safety critical software. What practices you should follow, what documentation you should produce, how you should verify and validate that you've done the things the correct way, and things of that nature. So they basically tell you, here's some standards about how you are supposed to do your software. Then they give you risk management processes and procedures, how you analyze for risks, how you mitigate for risks, how you reduce the likelihood of risks. That's called abatement. And they have both a top-down and a bottom-up type of a way of classifying these things. In other words, you can look at the code and then work from there, or you can look at the overall system function and work from there. There's ways of classifying risks and categorizing risks and all that kind of stuff. And each of these standards specifies these things in its own way. They also specify processes and procedures for other situations that are specific to the application. We'll see a little bit of that in a moment. Okay, one of the issues is coordination among all these standards. The people who develop all these standards frequently get together and talk to each other and try to use the same or similar terminology and redo their ways of describing things so they're similar to each other and things like that. There is some degree of coordination, but applications differ significantly, and therefore there are often major differences in the standards. And even within an application, there may be standards that are not necessarily well coordinated. This turns out to be particularly a situation with the medical community, because the medical people are very concerned about safety. And for decades, they have been developing standards, but they tend to develop them within a given country, and then they are not necessarily the same between countries. Sometimes it's difficult to navigate through all the applicable standards. For example, suppose you're writing software to implement a medical database and you're planning to sell it in both US and Europe. It turns out there are dozens of standards that you have to comply with in order to be able to sell it in each country. So the process of adhering to all these standards can be quite complicated if you are trying to sell your product in lots of different countries. So that's something that filters down to the software developer and the software designer, that they have to do this way for the Europeans, and they have to do it that way for the US standard, and that way for the Canadian standard, and so forth. Now, I've said this several times and I want to repeat it again. Software safety begins with system safety. You have to understand the system the software is part of. Software is always part of a system, a car, a database, whatever. If the system is harming someone, the software may be a factor in the system's ability to harm someone, and that's why you pay attention to the system as well as the software. So you typically begin your safety analysis by looking at the safety issues associated with the system. So in order to give you a flavor for that, I'm going to go through several of the well-known standards and show how they handle some of these things. And you'll see that there's some similarities and some differences. Let's start with the military and the nuclear power people who have used the same standard, MIL standard 882, for many decades. 882E is the latest version of that standard. And it defines a hazard to be any real or potential condition that can cause injury, illness, or death, or damage to property. Now, this damage to property thing turns out to be an interesting point, because some standards include it, some standards don't. Some standards only focus on harm to a person. Others are more broad and they worry about damage to the environment or to property. And that second part about damage to property or the environment greatly broadens your responsibility here. The nuclear power people in the military are very, very responsible in this area, in my experience. Mishap. A mishap is an unplanned event or series of events that results in death or injury. The difference here is the hazard is the condition that has the potential to cause a problem. The mishap is the specific situation that results in the problem. And you should understand that difference because your exercises may involve that, especially exercise 1. Safety is defined to be freedom from conditions that can cause injury or illness or whatever. In other words, they don't have hazards, so you don't have mishaps. The key idea here is that a mishap won't do any harm unless there's a hazard. You get rid of the hazards so the mishaps don't hurt somebody. The hazard is what might result in a problem. The mishap is the accident that causes it. The idea is you can't prevent mishaps. You can prevent hazards. Here's an example of a hazard. The guy is using an extremely dangerous technique to put up a safety poster, which is kind of weird. But anyway, the mishap is the actual accident. So let's review the difference between these two again. A parent leaves medicine on the counter. That's the hazard. It doesn't cause any problem. It's simply a potential for problem. The mishap is the child sees the medicine and starts ingesting the medicine because it tastes good or something. That is where the problem shows up. Now notice that if the hazard didn't exist, the mishap wouldn't have been a problem. The child would not have seen the medicine, or what they did see would not have been harmful to them. The hazard doesn't cause the problem, but it's the potential problem. Here's another example. Shrubbery hides a stop sign. That's the hazard. The car fails to stop and hits another car. That's the mishap. Smartphone has texting capability in a car. That's the hazard. The mishap is the driver does a text and then gets into a serious accident because they're paying attention to the text. Water is spilled on a floor and not cleaned up. That's the hazard. Someone slips on the water and breaks their arm. That's the mishap. So both of these situations have to happen in order for the harm to be done. But where you focus when you're designing your software is on the hazard. Nobody intended to cause injury or harm. The mishap was normal behavior under some circumstances. Like this example here, the hazard in this cartoon is the manhole cover that was left off. The hazard, that's the hazard. The mishap is the guy walking down the street and not seeing the manhole cover undone because he's carrying a big box. He can't see it. And you can see that there's going to be some harm about to happen. Okay. Now, here's a little bit more complex example. The hazard is a power plant was not designed safely, and therefore it catches fire. The mishap in this case is a complex sequence of events. An incorrect temperature reading causes a heater to go on, resulting in overheating of a chemical mixture, leading to a chemical reaction, producing excessive pressure, causing an explosion in a fuel storage area, producing a major fire in the power plant. Now, notice that the mishap can be a long sequence of events, but the hazard was the way things were designed. Now, you could claim that the incorrect temperature reading was in fact the cause of the problem, and that too would be potentially a software mistake. But designing the power plant so that such an error could cause an explosion is a more serious problem, and it's the hazard. And again, we have to think about designing the system, not just designing the software. Okay, now I'm going to switch gears and talk about the standards for aircraft safety. The standard here is DO 178, and that's now up to C. C is interesting because from a programmer's point of view, it's the first version of aircraft safety standards that recognizes object-oriented design. Now think about that. Object-oriented design began in the 1980s, is widely used in the software world by the 2000s, and DO 178C didn't come out till around 2010. That shows you how far behind the FAA is in the standards for aircraft safety. A failure is the inability of a system to perform a required function. It's defined as catastrophic. It would prevent continued safe flight or landing. It's called hazardous if it would reduce the capability of the aircraft or of the crew, but it would allow them to cope and avoid potentially fatal injury. In other words, catastrophic means there's nothing the pilot can do about it. Hazardous means the pilot may be able to do something about it, but it's going to take some effort. Major is significant discomfort, like a lot of people bounce around in their seats and maybe hurt themselves or something. Minor is inconvenience, like the heating system shuts down and everybody's too cold for a while or something. That's the way the aircraft people look at it. Now let's switch to NASA. NASA has their own standard, 8719.13c. And in NASA, they look at it in an entirely different way. They look at safety of the process you use to develop software and technical safety requirements for the mission they are about to accomplish. And that translates into specific techniques for software design and development that the software must do because of the safety requirements of the mission. Okay, now it's time for exercise 1. And we are a little earlier, but that's okay. The idea of exercise 1 is that each student is assigned a scenario. There's a handout available to you that has your name next to a exercise 1 scenario. And then there's another handout that describes each scenario. What you're expected to do here, by the way, all these scenarios relate to the COVID-19 virus. I just thought I would put something that related to something that's currently of interest. What you as a student should do, and you're going to have a break of half an hour, and that gives you time for a break plus time to work on exercise 1. So we'll resume at about 25 after 10. Anyway, you will, during the break, you will identify 3 ways in which software might contribute to a safety hazard for the scenario assigned to you. You will discuss the hazard and how software can create that hazard, and then describe a mishap that might cause a safety problem because of that hazard. It says here 10 minutes for the break and 10 minutes for the exercise, but I'm giving you an extra 10 minutes because we're a little early today. I guess last year, Dr. Wong had a longer introduction, but whatever it was. Anyway, so we'll have 30 minutes instead of 20. And so 25 after 10. And each of you in turn will turn on your microphone and give a brief presentation to the class. Here's the 3 hazards, blah, blah, blah. And here's the mishaps by which this hazard might cause a problem. It should take you about less than 5 minutes to do that. The idea is not to have a long presentation. That will be on Thursday. Today, it's just, here are the 3 hazards I've come up with, and here are the mishaps by which they may cause a problem. You should spend at least a minute or so explaining the scenario that you have been assigned, because the other students will have looked at their own scenarios. Okay, so that's the situation, and you can take your time now for break and exercise 1. It says 20 minutes, but I'm giving you 30 minutes. So I'll see you all at 25 after. Okay, I think it's about time to start again. What I'm going to do is I'm going to stop sharing, and then we're going to go down this list here. And we'll start with Nicholas Chow, and you share your screen and then give your presentation. So go ahead.
What exactly should I be sharing on my screen?
Well, just yourself if you don't have anything else to do, but basically we need to hear you and maybe see you.
Okay. So for my first hazard, I talked about like how the opening and closing of the containers might be dangerous if the viruses transfer like airborne and the software is not correctly timing the opening and closing of the sample. So a mishap could occur if the software causes the tube to stay open while a scientist with improper PPE goes in and then he gets infected with the virus.
Okay, would you please briefly explain your scenario, because the other students may not have read yours.
Okay. My scenario is that scientists are studying viruses that are in tubes, and they're studying whether or not they could harm humans or animals. They'll add substances to invoke genetic modification. And that's basically it. There's a lot of samples in tubes and it
Okay,
spins
that's
around.
fine. So we understand your scenario. Okay.
And then, so for my second hazard, I said how the spinning of the tubes might cause leakage if the viruses are in water and the software is controlling if it spins or doesn't spin, or if it could spin too much. And so a mishap could occur where the tube doesn't spin and a virus that's already been genetically modified is modified again, or again with a scientist with improper PPE goes in and it spins out of control. If the virus is sitting in water, it could get on him and infect him. And for the third hazard, they're adding substances to this virus, so they're creating different and stronger viruses, and the software is controlling how much of that substance is being added. And so a mishap could occur where the software adds too much of a certain substance and makes the virus mutate in a way that's extremely dangerous, and they can't record what they were intending to record.
Okay, that sounds very good. Bob Lou? Is
Hi,
Bob Lou
Professor.
here?
Hi, Professor.
Okay,
Sorry, I missed the questions that we are supposed to explain.
well, you're supposed to have done this work for the last 20 minutes.
Yeah. So we are talking about which one? Because there's a couple of scenarios that I went through.
Well,
Virus
it's that-
testing lab, virus research lab.
Did you see the list that shows which you're assigned?
Yeah, virus testing lab.
Yeah,
Okay, so I went through almost all of them just to get a bird's eye view.
Okay.
Yeah, so for the virus testing lab, I think is the most hazard would be like, because there was an options that test samples were given for analysis. So there may be the quantity of the samples will be given to a machine, and that would be the important. If it is given excessive amount, that would cause some hazard because it may overflow. Opening the test samples in appropriate environment, that is one another thing, because it has to be open in test environment. If it is open in environment other than test, that may cause virus to go out and create a hazard for a human or any other animals. The equipment that we use for testing, that also need to be tested thoroughly, otherwise that would cause other problem as well. I think generating the test report is something that is very important and the end goal. So that has to be done as well. But the hazard, and I think on the test samples, opening and how we can dispose it properly, these are the two areas that we have to probably see most hazard on it.
okay. Wakil? If I pronounce your name wrong, please correct me.
It is correct. Can you hear me?
Yes, it's you.
Yeah. So my topic is electronic thermometer. This is a device that is used to take the temperature of people's, which basically checks if the people have a fever, and then if they don't have a fever, they can be able to enter the facility. Or if they have a fever, they can be denied from entering. Some of the hazard that can happen in this device is since the device it could have incorrect reading of like patient's temperature. So this could lead to false assumption of the patient's health. That means if the patient, let's say if the patient was positive, and then if the device predict the patient have no have no health problem or have no like a fever, if the temperature shows normal, so the patient could be engaged or like be around with other people. This could result in the spread of more of the COVID disease, since we're talking about the COVID case here. And if the patient, if the device predicts as like negative, and then if positive, if the person is negative, the person could be isolated for because of the fever, the device shows the result the device shows. So this could, the false reading of the temperature could really predict the person's whether to be around or not, and this could potentially cause having of the false results, and then it could potentially affect the person or the patients.
Okay. Next one is Corey.
Okay, one sec. I'm trying to figure out. I guess I don't need to share my screen. So I had treatment planning software, and I came up with 3 hazards. The first hazard being that the treatment planning software could give like a physician a false sense of confidence in a given treatment plan. A user would have to balance the real world experience of the physician and the plan of a machine trained on data. Corresponding mishap is one in which a physician entirely relies on the treatment planning software, which leads to an adverse reaction that would not have happened had the physician relied on real world experience. Another hazard could be implicit bias. There will always be factors left out of the data training set. And the mishap in this scenario also being a treatment plan that is not effective. Another hazard is the machine may be open to vulnerabilities, and because of the dire nature of medical treatment, an exploitable machine could be used by a bad actor to commit a serious crime.
Okay, that's an interesting one. Okay, Lisa.
Hi, so I have a medical diagnostic device. So the first hazard can be obviously an incorrect diagnosis. So the mishap would be the patient would then take the corresponding pills or medical procedures that are aligned with that incorrect diagnosis, and that can result in a decline of health or a possible death. A second hazard could be the person attempting to utilize diagnosis devices not trained correctly, and they could end up pressing a wrong button or inputting data incorrectly, and the mishap could be a patient incorrectly diagnosed or not diagnosed at all. This could lead in a possibly fatal death or incorrect medical procedures, depending on what issue they're diagnosed with. And then the third hazard could be a device not maintained properly or just old, leading in miscalculations or errors. And the mishap would lead to patient being given a wrong diagnosis or not diagnosed at all.
Okay, Ian. You have to turn your mic on. Are you there, Ian? Are you there, Ian? It says your mic is on. I don't hear Ian.
Oh. Oh. Hello? Oh.
It sounds like you're not loud enough. Do you have a way to increase the volume on your mic?
Hello? Hello?
Can you hear me? Your microphone is too low in volume. Do you have a way to make it louder? We're going to have to fix that problem for tomorrow. Dong Chen, maybe you can communicate with Ian.
Can you hear me?
and tell him that he needs to figure out how to get his system working.
Can you hear me?
Rochelle?
Hello.
Hello, we can hear you.
I was assigned the topic of equipment leak tester. As a brief description of the scenario, the tester is a machine that tests personal protective equipment, like gloves or masks, which had high usage during the COVID-19 pandemic. The tester machine could use pressure measurements within the volume and upon the surface of the equipment to determine whether the equipment is leaking. Here are the 3 hazards I identified and the mishaps that would cause the hazards. The first hazard is that the testing machine is modeled off the personal protective equipment, which is dissimilar to the actual shape of the equipment. For example, in an N95 mask, there may be a corner created by seaming or folding of the fabric, which is not accounted for in the model. The calculated volume would have variance from the actual piece of equipment. The mishap is that based on the volume, not all of the surface area is tested by the testing equipment, and the untested surface area is permeable and would allow for a leak. The second hazard is that the pressure applied to the volume by the machine is calculated above a level, which would create an equilibrium state. The mishap is that the pressure, if there was a leak, would decrease to a state of equilibrium to a constant level, which the machine would consider safe, and that there was no leak when in fact there was. The third hazard is that the pressure gauge only reads an initial value, which is static and does not register a final value. This is a mishap because the value never changes, and therefore the equipment is not thought to have a leak. Thank you.
Okay, thank you. Belay? Let me know if I pronounce your name wrong.
My name is Balai Rogasa. The topic is mathematical model. It's a software that stimulates the future consequence of various actions that can be proposed to reduce the spread of disease. Some of the hazard associated with mathematical modeling is physical modeling error, which is created due to uncertainty in the formulation of mathematical model and deliberate simplification of the models. In COVID-19 case, due to uncertainty formulation of the disease, uncertainty in the data creates inaccuracy in modeling, which results in assumption and estimation of inaccurate. This prevents the necessary step or actions needed to be taken to find a solution to the consequence of the possible disease. Results in uncertain formulation of COVID-19, which might be a false prediction of number of patients and how the disease will increase or decrease.
Okay, thank you. Gabriella?
Hello.
Hello.
My scenario was patient database. So in the scenario it's listed, it says this software maintains records of patients who have contracted a particular disease, as well as additional information, such as the results of various treatment options. Experts and practitioners rely on the accuracy of this data. So for my hazards, I started off with the software does not learn the proper correlations between diagnosed diseases and treatment options. Since the experts and practitioners rely on the accuracy of this data, the mishap would be that the patient does not receive the proper treatment and their disease goes unaddressed. The second hazard would be the software does not securely store other patients' personal data. The mishap then would be the scammers get a hold of the patient's data. They use accurate information such as their name, their age, what disease they've been diagnosed with, and what treatment they've undergone to send believable scams, possibly asking for payment that is not really something that was required of them. And these will be very vulnerable patients that are put in positions to be easily scammed. And the last hazard that I've come up with was the database cannot handle editing, storing, and sorting of data. So if the database does not have the proper functions to handle all of the data that is incoming for multiple patients, probably large numbers of patients, then you risk losing patient information. The mishap being patient information and results of testing is lost. then doctors do not have the information needed to recommend and move forward with treatment. And possibly patients may have to undergo testing again. And that can be very invasive, costly, and an ordeal for those patients.
All right, thank you. Teresa?
I got manufacturing process control. This software controls the manufacturing process for various medical equipment. Its purpose is to make sure the equipment is manufactured correctly. It controls such functions as the speed of the manufacturing process, the proper functioning of the various machines used to manufacture the product, and detection and response to situations where something goes wrong. 3 hazards I identified is, well, an obvious one being like if the assembly line for the manufacturing process is going at the wrong speed, and that is a hazard that could cause a mishap of like causing an accident or just a mess. Another one is that the software might overlook potential contamination with the medical equipment, and the consequence of that would make the equipment unsafe to use, or it could possibly cause harm to other people it's used by. The last one is if one of the machines it controls functioning of is jammed and the software doesn't detect it quickly enough, several medical equipment can be potentially ruined. Yeah.
Okay, thank you. Ian, have you been able to figure out how to make your microphone louder? Apparently not. Okay. Just as a heads up, you notice in the right-hand column of that list of topics, there's a list of exercise 2 topics. Tomorrow or Thursday, you will each give a presentation on your topic, and you will need to be able to display your screen, share your screen. It's usually a button right near the bottom center of the screen that you get from Zoom. And I'm going to go in reverse order. So those who went last today will go first on Thursday, just so you know. Okay, I will take over the screen now. And let me just get things back to where I need them to be. There, I believe you should be able to see my screen now. Now we're going to do part 2. We're going to do the safety process. Figure out how to get this thing to work. There we go. There is a basic process that pretty much all of the safety standards call for you to follow, with many details that are different. And it involves 4 steps. The first 2 steps are focusing on the system that you are building. The first step is to determine the hazards, as you did in the exercise you just completed. What can go wrong? The second step is to identify the potential mishaps, which you also just did. And then in addition to that, you identify the safety critical components of your product that might contribute to those mishaps or those hazards. So in other words, you say, okay, this might happen. This would be controlled by this piece of equipment or this piece of hardware or this piece of software. So this is the component we have to focus on to make sure it does its job right. The third fourth step are associated with looking at the components and figuring out whether or not they are able to do what you want them to do. So the third step is to determine what's called the probability of the component failing. Or as we will see in a moment, or actually Thursday, the other possibility is what's called a level of control. In other words, to what extent does the component contribute to the possible mishap or hazard? And then the fourth step is to take appropriate steps to deal with things during your development and testing processes. Now, just as a general picture here, this is the model we're going to use for most of the rest of the lecture, both today and on Thursday. Today, we are going to focus on the top two activities, the system analysis activities. On Thursday, we will hear from each student doing their own report. We'll talk about that later. But then we will also have a discussion of the third and fourth steps. So today we're focusing on analyzing what could go wrong, basically, and what could cause it to go wrong. And then on Thursday, we'll focus on what to do about it. Okay. So let's take a look at the safety process in a little more detail. This is done through words. You identify the potential hazards. You decompose the hazard, what's called the hazard threads. Those are the potential mishaps that could happen. And you break that down into more and more detail. That enables you to identify the components, including the software, that might contribute to those mishaps. Then this is something that's not in the diagram, but is very important. Link it to the requirements. Why is this important? Because very often what you find is that a hazard is due to the way the requirements were stated, or a potential mishap is related to that. And you may determine that the best way to deal with the problem is to change the requirements. Very often requirements are stated in a way that does not reflect a full thinking through of what the requirement might result in the way it was stated. The requirement might say something like never do this or always do that. And in the course of looking at steps 1 and 2, you may say, well, here's a situation where maybe we shouldn't do it that way. Maybe we should do it a different way. And so that may translate into a negotiation with the customer over what the requirements are. And sometimes that's the best way to solve a problem. Just slightly revise the requirements. Generate a mitigation strategy. Given what you're dealing with, you say, this is how we're going to do it. We're going to develop this part of the software extra carefully or some such thing like that. Implement that mitigation. In other words, do whatever you're supposed to do. And then verify that you did it correctly and it had the desired result. Now, this is another step that's not in the diagram, but it's really a very important part of what's called quality engineering. And that is, make sure that you did it right and make sure that having done it right, it had the desired result. And then it says document safety artifacts. What does that mean? It means all the notes and details and records you kept during steps 1 through 6 are fully documented and recorded. Now, why is that the case? Well, think about what happens after an airplane crash. The experts analyze what went wrong and then try to figure out what they did wrong when they developed the product that resulted in the accident. And what they end up doing is going through all these steps and seeing, did we miss something here? Did we miss something there? And so forth. And in order for them to be able to do that, they have to have documentation on what happened during all of these steps. An interesting little observation. I was once doing some research in this area, and I happened upon a website from a group of people who were doing extreme programming. And it was a question and answer site where somebody said, my company has the opportunity to bid on some safety critical software. Should we do it or not? And the answer was, don't do it because you'll have to spend a lot of time doing documentation. In other words, the people on that particular website did not want to have to do a lot of documentation in their software development. And the message was, then don't try to do any safety critical software. All right. Now, I want to talk about approaches to hazard analysis. There's what I call the traditional approach, which is treat it as a software reliability issue. And the idea there is take all that we know about achieving software reliability and apply it to our application and deal with what happens there. For example, we identify all the components that may fail or have errors in them that would contribute to a hazard or a mishap, actually. Use various approaches to make those failures unlikely. Now, for example, in the case of hardware, they might build a particular part out of extra strong material. Or in the case of software, they might develop it using much more rigorous development techniques. And then much of the analysis for doing this approach occurs during and after the design of the software or of the system. In other words, you've got a design, now you analyze it to see where could it go wrong and where could there be a reliability problem and what could we do to make that less likely to happen. Now, that's what I call the traditional approach. There's a newer approach called the system control approach. And the idea of the system control approach is that you identify ways in which the whole system might fail. And then you create system requirements and constraints that forbid those failures. And then you have a system that it can be implemented without necessarily failing in the ways you identified. The key thing about this is that this analysis occurs before you design the system. It occurs when you have the requirements. You know what it's supposed to do, and you say, well, here's how it could go wrong. Now, notice that the one on the left is sort of a bottom-up approach. You look at the components that might fail and then work from there. The one on the right is a top-down approach. You look at the overall system. It turns out that both of these are useful. And if you're going to do proper safety engineering, you actually do both of these. Now, I'm going to focus on the one on the left for the remaining of the lecture today. And I'm going to get into the one on the right more, although I'm going to say a little bit more about the one on the left also on Thursday. So we're going to start with the traditional approach. Software is a component of a system. Make the component failure unlikely and less harmful. In other words, develop very high quality software. That's what it boils down to. So we begin with the first step here. I determine the system hazards. And the way we do that is we do what's called hazard analysis. There's a name for it called FMEA, Failure Mode and Effects Analysis, which is a long term for figuring out what the hazards are. It's a reliability engineering technique that is used to identify the modes of failure, that is the different modes the system can be in that might lead to failure, the causes of those failures, and the effects of those failures. How serious are they? Interestingly enough, this is a topic that is not typically covered at the undergraduate level in most engineering schools. It's typically covered more in depth at the graduate level, if at all. And it's something I never learned until I was actually working for real companies where they were worried about the reliability of their products. Okay. This approach can be focused on the functionality, the design, or the process used to develop or produce the product. And that's an important point because it's not just looking at the code, for example, it's also looking at what functionality can the product do, how have we designed it, and what process are we using to produce it. So it really gets into many, many aspects of what you're doing. There is an additional element called failure mode effects and criticality analysis, where you add that little letter C. And what that means is that you pay a lot more attention to how critical the failures could be. In other words, how harmful they could be. Now, here's a sort of an example of a technique that might be used in this process. It's called fault tree analysis. You take the hazard and you say, what could cause this hazard? And you typically end up with several possible causes. And then you take a look at each of those causes and say, what could cause them? Or what could contribute to them? Either of those is possible. And the idea is you continue down this tree until you get to something that you could actually do something about. You could modify the code to prevent that from happening or keep it from being too big or whatever it might be, for example. The idea is, I've only shown 3 levels of tree because of the size of the slide here, but the idea is you go down to as much detail as you need to until you get to something you say, I can do something about that. Now, let's take an example. The hazard is the patient in the hospital may be given the wrong treatment. So how could that happen? Well, let's say you say one possibility is vital signs are reported, but they are erroneous. The machine that is measuring the vital signs of the patient, it has a bug in it and it is producing the wrong results. It claims that something exceeded some limit when in fact it didn't. Another possibility is that vital signs exceed the limits but are not corrected in time, maybe because the response wasn't quick enough. Now, let's take that one and look at more details. And unfortunately, I apologize for the lines not coming out quite right. I had trouble using PowerPoint to get it to come out right. But one way the vital signs could exceed the limits and not be corrected in time is that the frequency of the measurement is too low. In other words, you're not measuring the vital signs often enough so that when they exceed some limit, it takes you a while to even notice that they have exceeded a limit. Another possibility would be that the computer recognizes the limit, but somehow fails to raise the alarm. Maybe there's a bug in the software that causes the alarm not to be turned on. Or another possibility is there's a failure in a sensor so that you don't notice that something has exceeded a limit. Or another possibility is that the nurse does not respond to the alarm in enough time. Now, those are 4 ways that that problem could occur, vital signs exceed limits. And the idea is then you, for each of those four, you say, is there something I could do? Like, for example, on the nurse responding, you could say, well, we either need to have more nurses or we need to have some kind of a nurse alarm system that assures that a nurse shows up within so many minutes or something. Sensor failure, okay, you look at this failure, ways the sensor could fail and go into details on that and so forth for each of the options. So that's how this failure mode analysis works. The idea is you go down this tree until you get to things that you can actually do something about, and then you do whatever it is you should do. Now, this is an example of a list of possible hazards for a major system. And the only reason I'm showing it to you is to show you the scope of the sorts of things that could happen. In the exercise the students just finished, each of you pointed out several hazards for your particular scenario. And you'll notice that there were an awful lot of ways that things could go wrong. And so when you do the hazard analysis, you usually have a very long list. So that's why I'm showing you this, just to give you an example of a long list. And this is probably not even all that long a list compared to some of them that I've seen. Now, you've determined the hazards, done the analysis, understand how severe the potential consequences are and so forth, and figured out maybe what might contribute. Well, the next step is to go into more detail in identifying what the critical components are and what the potential mishaps are. Now, let's look at identifying the components. A component that might contribute to a hazard if it fails is what's called a safety critical component. If this thing breaks or if this software has a bug, then we might have this problem. Note that most hazards in a system have many components, and therefore there may be many components that might contribute to a hazard. This software could have a bug, or if you have the software consists of 15 modules, maybe 8 of those modules could have bugs that might affect the hazard. If you have a piece of hardware, there might be several different moving parts, any one of which could fail, things like that. And some components may, of course, be software things. Software is often used to replace mechanical or human controls in many products today. So the amount of times that the software is responsible for the hazard or the mishap has been getting larger and larger over time. It's kind of interesting. When I first went to work for Texas Instruments in the 1970s, something like 1 out of 20 technical people that they hired were software developers. And by the time I retired in 2010, it was like half the people they were hiring were software people. That was a huge difference in terms of how many people they needed to write software. And it probably would have been larger than half. In fact, probably is larger than half by now. It's just that they had a lot of products that required a lot of electrical and mechanical engineers. But anyway, that's just an observation. When software controls something, it is often potentially safety critical. And so an awful lot of software controls an awful lot of things today. But that's not the only way that software can be safety critical. It gets to be a little more complicated than that. Here are some things that may be safety critical that software is in charge of. Assessment of system health. For example, redundancy checks on data transmission, range checks within the software, CPU health assessment, software safety critical devices often is checking the hardware to see if there's any indications of hardware problems. I was involved in the very early days of designing microcircuits so that they would send out a signal to the software if there was a hardware problem or if something was overheating or anything like that. Power up and runtime monitors. Well, there's all kinds of things that go on in software that are simply checking the health or the solidity of the overall system. When you boot up a computer, one of the things that goes on is that your operating system checks to make sure everything is working correctly, for example. So if that were to fail, it might lead to a safety problem. Enforcement of critical timing. There may be some activity that you're involved in that has to happen at where time is really important. A really good example is one that I'm familiar with, has to do with nuclear power plants. In a nuclear power plant, you have software controlling devices that do things like check the temperature of things and the height of some liquid in the container. And things in a nuclear power plant happen so quickly that software often needs to be checking something every microsecond or even more often than that. And that's pretty often. And so sometimes you have applications where the timing really is critical. If you've ever written software to control an engine, there's an awful lot of critical timing in connection with that. This has to happen exactly so many milliseconds after that happens, kind of thing. Exception trapping and handling of various kinds of exceptions and interrupts and failure signals and what have you. So that turns out to be very hard software to test because you have to have a hardware failure in order to have the conditions under which you test it, unless you have some kind of a simulation of the hardware. I remember once working on an application where we had an error for an interrupt from an unknown device, and we didn't know how to test it because we didn't know how to create an interrupt from an unknown device. Well, one night we were working away at this thing, and there was a thunderstorm and lightning hit the building, and all of a sudden we got an interrupt from an unknown device. So we were able to test that software, but it was purely lucky. Okay. Functions that execute the system's response to a failure. That's another thing that's not necessarily easy to test because you have to have the failure in order for that part of the software to be called upon. But nevertheless, that's an area where if that thing doesn't respond correctly, then you have a problem. Here's some more ways that software can contribute to a problem. Functions that enhance the system's survivability may not work right under some circumstances. So systems that keep the core functionality functioning or safe, something that keeps data safe if you detect an intruder, that sort of thing. Data quarantine and sanitization functions, where you're keeping data away from certain, we had the example, one of you had the example of the database where somebody hacked into the database and used it incorrectly. That's sort of what this is talking about. The range and reasonableness testing that you go on. You're supposed to search through n elements of a metric. So, well, you check to see if n is a reasonable number. Tamper proofing and cyber attack proofing. Authentication, especially for any action that is potentially lethal. I ran into this with military equipment. An awful lot of military equipment is extremely lethal, and there's an awful lot of safeguards built into them to make sure that the person trying to pull the trigger, so to speak, is authorized to do so. And the reason is just because you don't want somebody accidentally doing something that's lethal. Inhibiting functions and interlocks. Those are all examples of ways that software might influence things. Now, here are some specific examples. And these are, again, these are examples of general categories. The first example is an incorrect safety critical alert. In other words, you send an alert that is incorrect or it shouldn't have been sent. You send an alarm that should not have been sent. It was accidentally sent. And or you fail to send an alarm when you should have sent one. Either way, it may cause all sorts of mishaps. Either an alert wasn't sent when you should have, like your smoke alarm didn't go off, so you didn't realize your house was on fire, or you send an alarm that's causing a bunch of fire people to show up to your house when your house isn't on fire. And maybe that's not as bad a problem, but you have some applications where that sort of thing could be a real problem because maybe those resources are needed for some dealing with some other house or something. And the example that I'm familiar with is with an air traffic control situation. You either fail to warn the air traffic controller of an imminent collision between two airplanes, or you tell the air traffic controller there is an imminent collision when there really isn't. And either one can cause all sorts of undesirable consequences. All right, the second example is incorrect data. You transmit data that has an error in it. And the interpretation of the data might lead to an incorrect consequence that might do somebody some harm. For example, you send a tornado warning, but it gets misspelled and it gets received as to-do warning, and the person, or to-do waning, and the person on the other end says, what is that all about? And they don't realize there's a tornado warning, so they don't take care or protection. They don't seek a safe place to go, and then the tornado hits and they're harmed because they weren't warned about the tornado because of a data mistake. You transmitted the data incorrectly. Third example is safety critical related data in a database is corrupted. I often tell students, what happens if the university you got your degree from loses its record of you having been a student because of a database failure? When will you notice that failure? Chances are nobody will notice it for many, many years. Maybe 10 years later, you apply for a job and you say, I got a bachelor's degree from so-and-so university, and they check and the university says, we have no record of that student having been here. The real risk with this sort of thing is that often you don't notice the corrupted data for a long time. And by the time you do, it's a real mess sometimes straightening it all out. This is why we have backups, for example. But anyway, the idea is you just have bad data in the database, and therefore what it's telling you is incorrect. And I think one of the students had an example of that. Another example is you didn't transfer things correctly. You didn't do the proper error correction code checks to make sure that you did it. You followed the wrong protocol or something like that. It's similar to the bad data, but in this case, it's not that you just transferred the wrong data. It's that you followed the wrong protocol, and therefore the communication was screwed up. So you said increase the pressure to 200, but it was received as increase the pressure to 2000 because of a protocol mistake. Another example is a timing or interrupt failure. In other words, you're supposed to do something within 1 second. Like I was on an application once that had a clock, and once every second you increase the clock by 1 second. It was pretty obvious. And if you screwed that up and didn't increase the clock correctly, you had the wrong time. So that's an example of not responding to an interrupt at the right amount of time. Sometimes things that are complicated involve an awful lot of synchronization. For example, communicating between the computer and a peripheral device sometimes involves a lot of very careful synchronization. Okay, incorrect modes. Now, this is one that I'm going to talk about today, and then I'm going to talk about again on Thursday. The idea here is that there are some applications that have different modes of operation. And the one that I'm going to use as an example is software that its function is to both to operate a helicopter and to train people to operate on a helicopter. So the software has two modes. It's in operational mode where everything you do actually causes the helicopter to fly or whatever. And you have a training mode where everything is designed to behave as though the helicopter is flying, but you're actually not doing any flying. You're just training people on how to use the helicopter, how to fly it. And the example is you think you are in training mode, but you accidentally switch it to live mode. And then during your training exercise, you fire a weapon or something, or start something going that shouldn't be going in a training scenario, and you might do some harm. That's an example of an incorrect mode thing, where you suddenly switch the mode flag or something, or fail to read it correctly or whatever. Okay, now let's talk about some software safety problems that are very common, and in particular, the reasons for those problems. Turns out that over 70% of test failures are attributable to requirements problems. Either the requirements were not stated correctly, or they weren't communicated correctly, or they weren't understood. And a classic example that I ran into is you have somebody called a system engineer who's designing a system, and he writes requirements and expects the software developer to read those requirements and do something, except that the software developer doesn't speak quite the same language as the system designer. So the system designer tells the software person to do something, and the software person interprets it incorrectly. It's a perfectly innocent, incorrect thing, but the problem I used to have is that I used to be in a position where I was trying to get the system designers to be more explicit and detailed in their requirements, and they didn't want to. They said, well, anybody knows that. I don't need to spell it out. But it turns out they did need to spell it out, because the programmers often didn't understand it and didn't necessarily know what it meant unless it was spelled out. An example that I remember particularly well was, again, it gets back to a nuclear power plant. The nuclear physicists were stating the requirements, and they said, we want you to check this water level to make sure it doesn't overflow. And they didn't say how often to check it. Their attitude was, well, anybody working in a nuclear power plant should know. Well, it turns out the programmers didn't know. And so they were checking the level once a second. They thought that seemed reasonable. It turns out that should have been checked every once per millisecond. And in a nuclear power plant, 1 second is a long amount of time. An awful lot of bad things can happen in a nuclear power plant in 1 second. And it was discovered by a person who was doing a review of their software. And I remember there was a guy who lived in Canada, and he said, I did this check and I pointed out the problem. And he said, I suddenly became very concerned about the safety of the local nuclear power plants, because all these people were writing all this software without knowing enough physics to realize that what they said when they said check the water level meant something specific, but the physicists didn't think they needed to bother telling them, and the programmers thought they needed to know. So that's an example. In this situation, the software is correct according to how the software developers understood the requirements, but the requirements were either wrong or misunderstood. And this last one is important too. The requirements changed. One of the most common problems in real life situations is that somebody changes the requirements when they're halfway through the project. And it causes all sorts of consequences, but nobody understands all the consequences. And so you change the requirements, you think you've corrected for them, but you realize there's something that should have happened during the design step or whatever that didn't happen, or maybe the test code wasn't modified to properly test for the new requirements or some such thing like that. Okay. Almost all software has a problem in the area of requirements. Getting requirements right is difficult, and most software developers don't particularly like doing it. They would rather be writing the code or designing the system. But it turns out this is really where most of the problems start. And it's especially true for large and complex systems. For example, I was once working on a system that was basically a local area network and a bunch of software for a military tank. You know what a tank looks like. And the problem was that there was a bug that caused the top of the tank to rotate. Now, the problem is when the top of the tank is rotating, you can't get into or out of the tank. The way it's set up, you can't do it. So this tank was rotating because of a software bug, and nobody could get into the tank to stop it. And all the software was inside the tank, and there was no communication with the outside world. And the only way they could fix the problem is they had to wait until the tank ran out of fuel and stopped of its own accord because it didn't have any fuel left, which took like 2 days. And then the top quit rotating and they were able to get inside and start working on fixing the bug. But anyway, getting the requirements right is really a very crucial step for all software, but especially for safety critical software. Notice this last bullet here. Some requirements are derived from design decisions. Sometimes you have to alter the requirements or add to the requirements. These are sometimes called derived requirements based on how you've designed the system. Or you can even do that when you're writing the code. You can make a coding decision that causes you to have to add to the requirements. Requirements tend to change, and understanding how to respond to that is a big deal. You have to have, there's something called a requirements trace tool, which is complex to set up, but it basically says this requirement leads to these design elements, which leads to these coding elements and so forth. Or these tests that have to be run and this test code and all kinds of these implementation details, this method of installation, all that. And then if you change a requirement, you can then figure out what other things need to change. And that's really important in a safety critical type situation. Another thing that has been discovered is that many errors occur at what are called organization boundaries. In other words, one organization tells another organization what they're supposed to do, and things get lost in translation, so to speak. I already gave you the example with the system engineer or the scientist in the nuclear power plant talking to the programmer, but it can get a lot worse. I was once working on a product for Texas Instruments. At the time, I was employed at Southern Methodist University, and I was doing a project for Texas Instruments, and Texas Instruments was building its product for the US Navy. And a particular requirement was coming from the Navy Research Lab. So the Navy Research Lab told the Navy told Texas Instruments told me, and by the time I got the requirement, it didn't make any sense. And the only way I could fix it was to find the guy in the Navy Research Lab and figure out what he really wanted. And once we worked that out, everything came out okay. But the point is that the requirements got communicated incorrectly because of all the different organizations it had to go through. Okay, let's look at how that happens. Customer says something, here's what I want. They speak in their own terminology. Goes to a system analyst or a system engineer. The systems analyst and system engineer is supposed to understand the customer's requirements. They define requirements for the next level down in terms of the way a systems engineer communicates things. So it's somewhat different terminology. The software analyst reads that and translates that into requirements for the software developers in software terminology. And the software engineer develops the software. The problem is there's many steps in that process and many ways that things can get lost in translation. Okay, why do errors happen at organizational boundaries? Because there are different cultures, different ways of organizing, different vocabularies, different terminology. And I've run into this statement so often. It's obvious that something or other should be the case. Well, it may be obvious to the person stating the requirement. It may not be obvious to the person responding to the requirement. Here's the example I talked about in the nuclear power plant. The physicist says, you must check the water level. And the programmer says, I think once a second should be fine. And what happened is the physicists thought it was obvious how often you should check. In fact, it wasn't obvious to the programmer. That sort of thing happens a lot. Okay. 85% of the requirements errors occurred at organizational boundaries. Remember, I talked about how many of the problems ultimately were due to requirements. Well, most of those are due to organizational boundary issues, which why I'm spending so much time on this. Software engineers often did not understand what the system designers thought were obvious. Timing issues, mathematical issues, statistical issues, whatever. Then, to make it worse, the requirements often change without assessment of the consequences. I have a true story here. We had a project that came out in phases, and there were like 10 phases. And each phase, we were up to about phase 3, each phase had been late. And in each case, the lateness was blamed on the software people not getting their job done in time. And a particular lady was the head of the software team. And so at the end of the 3rd phase, she was giving a presentation. And the general, and this was a customer, was the US Army, said, I want to know what I have to do so that you will get the phase 4 done by the deadline. And she said, you only have to do one thing, General. Anytime anybody changes a requirement, you have to get a signed document from me telling you what will be the consequences of this change on this project schedule and cost. And I will provide the consequences if you will insist on having that information before you approve the requirements change. And the general said, that sounds reasonable. I'll do it. And all the systems engineers were really upset because they were used to making changes without getting approvals. Well, turns out that one thing enabled them to get things done on time. Because whenever they proposed a change, the system engineer might say, oh, this seems like trivial. The software engineer, the software manager said, no, that change will add 3 weeks to the schedule. And the point was that they wanted the people making the changes and requirements to understand the consequences of the changes. Okay. Now, the second most common sources of software safety problems are design and coding errors, usually resulting from poor code structure that makes it hard to understand. And as a matter of fact, an awful lot of the problems occur when somebody other than the original developer is asked to modify the code and they don't understand it because it's not well documented or not well structured. Sometimes it's requirements that are hard to implement. For example, suppose the requirement says there should be no single point of failure. That turns out to be an impossible requirement to satisfy. Timing errors, syntax errors, all the kinds of things that programmers can do by mistake could contribute here. Bugs don't necessarily map to failures, by the way. Many bugs only have minor consequences. Others have catastrophic consequences. Okay. Now, the underlying causes of a lot of software safety problems are the change control process, where you make changes that introduce errors, often because you didn't follow the change control process the way you're supposed to. You're supposed to understand the consequences of the change and make all the necessary updates or corrections. For example, you change something in the software may mean that you have to change the way you test the software. The testing process, often safety-related testing, is not performed at all, or not performed thoroughly, or not really tied into all the rest of the development. Hardware failures. All kinds of things can happen to hardware, and if the software is not designed to appreciate that these hardware failures are happening. I mean, think about the human body. When you have a broken part of your body tells you by sending all those painful signals to your brain. In a hardware system, you want the hardware to tell the software. The software can be thought of as the brain. You want the hardware to tell the software, I've got a problem here. This part of me is overheating, or whatever it might be. And you can design things that way, but very often people don't. Okay, now we're talking about exercise 2. And then that'll be the end of today's lecture. Now let's talk about exercise 2. Exercise 2 is your opportunity to do some safety research. And you will do this research. You can use the library anywhere, or you can use the internet. Most of you will probably use the internet. Each of you is assigned a specific safety topic. You have seen that in your list that you used for exercise 1 on the far right-hand column. Your job is to research the topic and prepare a presentation about the topic that will be presented to everybody else in this group. In other words, to me and to all the other students. You will give the presentation at the next session. You will have 10 minutes for your presentation. Now, in the past, most students have stuck within 10 minutes, but occasionally you get a student who really gets into this and starts giving a 15 or 20-minute presentation. So I'll caution you to try to aim for 10 minutes. The goal of the presentation is to give the other students a good idea of some of the software-related safety issues associated with your specific topic. And the reason I'm doing it this way is because they are all very different. And some of the issues are quite unique to the specific application. Now I'm going to illustrate what your presentation should look like by giving you an example that's not on your list. And there is a template for this presentation that's available to you that you can use and modify to do your own presentation. Most students just take the basic template and edit some of it. A few students have done all sorts of very interesting graphics and things. One student even had a video, but you don't need to do all that if you don't want to. The idea is to just give the 10-minute presentation. So the first slide will be the title of your topic. So you can put your name here instead of sample student. You can put your topic here, and you can change this if you want to. But the idea is this is just your first slide. Your safety topic goes there. Your name goes there. Now, the second slide is its purpose is to introduce yourself to the other students in the class. So my name is, fill in your name here. Here's where I'm from. Here's what I major in. Here's a little bit about me. And I'm not saying you have to do it exactly like this at all. Most students do something rather creative at this point. But the idea is to introduce yourself to the other students and to me. Now, this slide is one where you talk at a high level about the different kinds of hazards associated with your topic. In the topic I'm showing you here, the topic is safety for children, and therefore it lists all kinds of things that can lead to problems with children, safety issues. But in your case, your topic will be airplane safety or ship safety or dam safety or whatever it happens to be. And so having done your research, you will be able to make a list of very serious potential hazards associated with your topic. The next slide gives you a little more detail about specific kinds of things that can happen that are software specific. In other words, the previous slide was general about hazards. This one is getting into software being involved in those hazards. So in this example, here's a list of things that software is involved in that contribute to hazards. Now notice on the previous slide, a lot of these things didn't have much to do with software. This slide is more broad, a broader look at things. This slide is more focused on software. These are things that software typically is involved in that may have to do with my topic. And of course, this list will be different for each topic. And you may say whatever you want to on this slide, and you can embellish it on this. The next slide is some specific software issues. Whereas this previous slide said, well, yeah, these are things that software may be involved in. This is examples of where software can cause a problem. Proper response to power failures in this example. Detection of hardware damage. Operate error should be uncommon. In other words, you have to have a very easy to use user interface and things like that. And again, you may embellish this topic more based on your topic. But the idea here is we started with very general hazards, then hazards that may involve software. Then now we're getting into some specific examples of where software can cause a hazard. And then you have questions and let the rest of the group ask you questions. So that's the basic outline of your presentation. 1, 2, 3, 4, 5, 6 slides. There's not a whole lot there. You're free to embellish things. So sometimes students will take one of these slides and expand it to 2 or 3 slides and show some specific examples That's fine. But the key idea of this presentation here is for you to study, do research on whatever your topic is. And you can, like I said, start in the internet. That's probably the best place to start here. And then go ahead and prepare this. That is what you will present on Thursday. There's a certain point in the presentation where you will each present. And for Thursday, you will have 10 minutes per student. So that's about an hour and a half for all the students. And so essentially what's going to happen Thursday is the first hour and a half is going to be more lecture, finishing up what I've been talking about. The second half will be the student presentations. And you should also send your presentation in so that we have it in the database here at the university. I have discovered some very interesting things in student presentations about different kinds of safety. And it's useful to me. I find it sometimes quite helpful to get that information that students present. Students sometimes uncover examples of hazards that I wasn't aware of, for example. Okay, that's the end of part one, and that's the end of today's lecture. We finished about 5 minutes early, but that's okay. I'm sure you won't complain too much about that. That's the end of what I'm going to say today, and therefore we're going to go back to all of us being here. I don't know if anybody else is in here except me, and oh, there we go. Mr. Lee, are we going to do anything before we tell the students to go away till Thursday? Are you there?
Professor, I have a question for you.
Okay.
So I know we have to present on Thursday, and that part of the research, we will be only looking for the hazard, not any solution for the hazard, how to prevent the hazard.
Now, that's an interesting point. You're welcome to do the solution to the hazard so long as you try to stay within the 10 minutes.
Okay.
All right.
Yeah, I feel that this covering both positive and negative test scenarios will be more than enough. But yeah, it's a good point. I probably would try a little bit for the the measures to prevent the hazard as well. Thank you.
Yes. Okay. Anybody else have anything they want to ask? Ian, I don't know if you can hear me, but your microphone wasn't loud enough today. We need to figure out how to fix that for Thursday. And with that, I guess it's time to close down for today. So I'll see you all on Thursday.
Thank you.
Thank you, Professor.